Early observations estimate its nucleus to be around 20 kilometers wide, a behemoth weighing over 33 billion tons. Yet despite its intense outgassing, Atlas shows nearly zero non-gravitational acceleration. It's like watching an engine fire with no recoil. If Loeb is right, we could be witnessing the first interstellar visitor that decides to stay. And ironically, when that defining moment comes, we won't even be able to see it. Because on that very day, Atlas slips behind the sun, swallowed by its blinding glare. Earth, the sun, and this enigmatic traveler align perfectly, leaving our planet on the wrong side of the light. For 6 long weeks, the most massive interstellar object ever detected will move through space completely unseen. No telescope on Earth will be able to track it. No sensor will record its path. For astronomers, it's like a cosmic blackout at the exact moment the universe turns the page. This isn't just a gap in the schedule, it's a disappearance at the story's climax. The perihelion, the moment of closest approach to the sun, happens during this blackout. If something unusual happens, a shift in trajectory, a burst of thrust, a gravitational slingshot, we'll have no eyes to witness it. The sun's light, 400,000 times brighter than the comet's glow, erases all traces from view. Even space observatories like Hubble and the James Webb Space Telescope must turn away, their safety protocols locking out any observation near the solar furnace. From late October to early December, all visual data, motion, brightness, composition, will go dark. For most of the scientific community, the window slams shut right when the mystery deepens. Only a few solar probes, designed to study solar storms, not distant comets, might catch a glimpse. But their instruments weren't built for this. Atlas will be far too faint for them to detect more than a flicker. In practical terms, the universe itself draws a curtain. Avi Loeb calls this period the silence before revelation. Because when Atlas reemerges from behind the sun, everything could be different. Its orbit, its motion, even its chemical fingerprints. The blackout isn't just a pause in observation, it's the calm before something extraordinary. Welcome to Lumora, where science meets mystery. Tonight, we step into the darkness with 3A Atlas to uncover what might happen when an interstellar traveler vanishes into the sun's shadow. When the first data on 3I Atlas came in, Avi Loeb's attention locked instantly on a single number, 20 kilometers. For comparison, the first known interstellar visitor, 1I Oumuamua, measured less than 0.3 kilometers. The second, 2I Borisov, was barely a single kilometer wide. But Atlas was a giant. The difference wasn't small, it was exponential. The Atlas team didn't estimate its size by guessing. They used its brightness, distance, and solar reflection models. The math left no room for illusion. The nucleus was massive. But with that number came a paradox. A body this large should behave differently. Comets of such scale usually show strong non-gravitational acceleration, tiny pushes from gas jets that act like miniature thrusters, shifting the object's orbit ever so slightly. Yet, across thousands of positional measurements, Atlas showed none. No drift, no curve, nothing but the steady pull of gravity. For a comet emitting hundreds of kilograms of gas per second, that's almost impossible. Outgassing should nudge it off course, the same way exhaust pushes a rocket. But if Atlas truly weighs over 33 billion tons, those gas jets would be too weak to move it at all. The math only works if the nucleus is not just large, but incredibly dense, almost like metal or rock instead of fragile ice. Loeb's team ran simulations. For any nucleus smaller than 5 kilometers or less dense than 1,000 kilograms per cubic meter, Atlas should have already drifted far from its predicted track. Yet it hasn't. Every data point sits perfectly on course. That precision, too perfect for a natural body, is what raised eyebrows. Astronomers proposed alternatives. Maybe the outgassing is balanced in all directions, canceling out the net thrust. Maybe it's a cluster of smaller fragments moving together, creating the illusion of stability. But both explanations require extreme coincidence, physics tuned with surgical precision. The mainstream model insists it's still a comet. An unusually stable one perhaps, but not beyond the laws of nature. Loeb, however, calls it an invitation to question our assumptions. In science, when every natural explanation begins to sound like an excuse, something deeper might be at play. And the contradictions kept piling up. Survey data from the Pan-STARRS, Atlas, and Vera Rubin observatories all suggest that smaller interstellar visitors should be far more common. For every giant object, there should be thousands of tiny ones, but the record shows only 3. If Atlas is typical, the night sky should already be filled with smaller cousins. It isn't. The odds of finding such a massive object first are less than 1 in 10,000. So either the universe is hiding an invisible population, or Atlas is an exception that defies every prediction. Loeb calls it the statistical anomaly that refuses to go away. And if the numbers don't add up, maybe that's because we're not counting everything that's really there. Trajectory maps for 3I/Atlas reveal something that shouldn't be possible for a random interstellar visitor. Its orbit hugs the solar system's ecliptic plane, the same thin disk where the planets travel, tilted by only about 5 degrees. For an object arriving from the void between stars, that kind of alignment is incredibly rare. Most interstellar bodies come in at wild angles, slicing across the solar system's plane like cosmic darts. But Atlas doesn't slice. It glides, almost perfectly parallel. When orbital analysts first plotted its course, they noticed something even stranger. In the weeks before it disappears behind the sun, Atlas threads a path of close planetary encounters, as if following a carefully laid sequence. On October 3rd, it passes just 29 million kilometers from Mars, a near miss by interplanetary standards. Then, not long after, it drifts close to Venus. Later, its trajectory brings it within reach of Jupiter's immense gravitational field. 3 major planets, lined up for near flybys within a single orbital window. The probability of that happening by chance is vanishingly small, less than 1 in 1,000. According to NASA's orbital dynamicists, each planet on its own could perturb the comet's path slightly, but the alignment of all 3 in sequence forms what some have called a gravitational corridor, a series of subtle tugs that could, if timed perfectly, shape its motion like a slingshot. For natural comets, such choreography would be luck bordering on miracle. But for Loeb and his colleagues, it's exactly this pattern that keeps the debate alive. The trajectory looks tuned, like a spacecraft using planetary assists to adjust its velocity before a decisive burn near the sun. As Atlas approaches perihelion, its closest point to the sun, the geometry becomes almost poetic. The orbit curves through the gravitational wells of multiple worlds, then dives toward the solar furnace at a perfect angle for maximum energy transfer. If anything were to happen, a change in speed, a directional shift, even a brief burst of propulsion, that moment would be the stage. But it's also the one moment when no one can watch. During perihelion, every Earth-based telescope will be blinded by the sun. Even the space observatories must turn away, leaving a gap in the data right when Atlas could, in theory, alter its fate. If the slightest change occurs during those hours, it will remain invisible until weeks later, when the object reappears on the other side of the sun and astronomers realize its orbit doesn't match what physics predicted. For Loeb, this blackout is almost poetic irony. The one moment when something extraordinary could happen, he says, is precisely the moment we're forced to look away. If the orbit is coincidence, it's one of the most elaborate in modern astronomy. If it's not, if there's intent behind it, then what we're watching isn't just a comet, it's a maneuver. And if that's true, the question isn't just what Atlas is anymore. It's who designed the path it follows. When the first detailed images of 3I Atlas arrived, they didn't look like any comet astronomers had seen before. Instead of a tail streaming away from the sun, the brightest glow came from the front, a concentrated luminescence facing directly toward the light. It made no sense. Cameras at Gemini South and the Very Large Telescope checked their calibrations, searching for a technical error. None appeared. The asymmetry was real. Weeks later, as Atlas drew closer to the sun, that forward glow faded and a more traditional tail emerged, as if something on its surface had changed. Perhaps a crust had fractured, exposing new layers of volatile ice. Or maybe something far stranger had occurred, a shift in energy emission we couldn't yet explain. Then came the chemistry. The James Webb Space Telescope managed to capture a few spectral readings before the blackout, and what it saw only deepened the mystery. The ratio of carbon dioxide to water vapor was nearly 8-to-1. For comets from our own solar system, water is almost always dominant. Here, it was barely present. The findings suggested that Atlas wasn't made of the same material as local comets. Its surface chemistry looked more like something preserved in deep interstellar cold or covered by a crust of frozen carbon dioxide that had barely been touched by the warmth of any star. At first, scientists urged caution. The readings were preliminary, but as more observatories confirmed similar data, the anomaly grew harder to dismiss. Was Atlas a relic from the outer edges of another star system, frozen for millions of years in cosmic night? Or was this something built, layered by intention rather than chance? In late September, just before the blackout began, another surprise emerged. Amateur astronomers across the world noticed that Atlas's coma, the gas cloud surrounding its nucleus, had turned a vivid green. Spectral analysis showed the signature of C2 and CN molecules fluorescing under ultraviolet sunlight. Most comets display this green hue near perihelion when solar heat peaks, but for Atlas, it appeared weeks early, burning brighter than any prediction. To the untrained eye, it was just a color change. To astronomers, it meant something fundamental was shifting: the release of gases from layers buried deep beneath the surface, or the breakdown of molecules never before seen in comets. Whatever it was, the transformation seemed too early, too intense, too perfectly timed before its disappearance. Each new discovery stacked uncertainty atop uncertainty: optical anomalies, chemical oddities, a spectral fingerprint that didn't fit any known category. By the time Atlas slipped behind the sun, it had already rewritten half the rules of comet science. And as the cameras went dark, one thought echoed through observatories around the world: if this is what we've seen before the blackout, what might be happening during it? The light faded. The mystery only deepened. October 29th, 2025. The date now marked in every astronomer's logbook. The moment when 3I/Atlas passes behind the sun. As it vanishes from view, Avi Loeb and his team believe that everything hinges on what happens in those hidden hours. At perihelion, the object will be traveling at nearly 44 kilometers per second, an interstellar bullet arcing through the sun's gravity well. If anything changes its velocity by just a few kilometers per second, that small nudge could transform its path forever. For most comets, this is where the story ends. A close pass, a flare of gas, and then escape. But for Atlas, this is where the real question begins. Because a slight change in speed, around 8 kilometers per second, would be enough to shift it from a hyperbolic trajectory to a bound orbit, keeping it inside the solar system indefinitely. Theoretically, that maneuver could happen naturally, but the odds are so low, the window so precise, that many scientists quietly admit, if Atlas does stay, it will look like someone meant for it to. Yet we won't know. The sun's brilliance blinds every instrument, even the most powerful solar coronagraphs, tools designed to capture faint light near the sun, can only detect objects much brighter than Atlas. For at least 6 weeks, it will be as if the object doesn't exist. Then, sometime in early December, it will emerge again. And when it does, its orbit will tell the truth. If Atlas reappears on the same trajectory, the story will fade into science, a rare natural comet, nothing more. But if it returns on a different path, something no gravitational model can explain, it will spark a new debate about what we're really witnessing. Because orbital changes cannot lie. They are physics carved into motion. NASA's lead small-body scientist Tom Statler draws the line clearly. It looks like a comet. It acts like a comet. Until proven otherwise, that's what it is. The mainstream community agrees. Comets are unpredictable, volatile, and strange, but not intelligent. Yet Loeb's perspective lingers. He isn't claiming proof, only that anomalies deserve attention. When an object stacks oddities, mass, density, alignment, chemistry, timing, one after another, it becomes irresponsible not to look closer. And that's what Lumora is all about. Between the known and the unexplained, there's always a gap, a shadow, where discovery hides. By December, when 3I/Atlas re-emerges from the sun's glare, the world's observatories will be waiting. If its orbit remains unchanged, it will return to the silence of space, just another cosmic wanderer passing by. But if it bends, even slightly, the universe will whisper a different story. Until then, all we can do is wait, watching the darkness where it disappeared, listening for the moment when science and mystery collide once more. This is Lumora, and the truth about 3I Atlas is only just beginning.